So today we are going to be talking about numerical approximation of ordinary differential equations. I produced this notebook that you can find in a place that I put yesterday in the WhatsApp. Maybe somebody can put it in chat. So you open it with the VS Code, for instance, and we can follow it. We are going to be using at the beginning. We want to solve this system, right? And we are going to do it numerically. And so we have to devise some methods to solve it. I'm not getting used to this, but I have to. And so we have a theory that we discussed yesterday that says this, right? That let me write it down here. If you have a point, you can find an interval. Point P, you can find an interval, a neighborhood UP of that, and an interval on the real line, C dot T, say, so that there is a solution, and a solution is a function from here to here, y, and we know because of the theorem that the solution exists through this point. Huh? And now we want to do approximation of this, let's say something like that, and on the other side. So we want to formalize what it means that we approach the solution, the exact solution, with this approximation. So we are looking for sequences of approximations, which we are going to call W twiddle. There are functions also here, so curves, and we want to say that this difference tends to 0 when I tends to infinity. Right? This is what we want. And here we are using a norm because we are thinking here that the y belongs to, and the f belongs to some vector space. Or can be also a patch in a manifold of Rn. So it's a piece of Rn in any case. So we are using some norm. But in practice, we don't work with this sequence, and you will never see this, basically. And for some applications, you construct this, but in general, you just stays with the points. So what we are going to compute is some set of points here along, like this. And then we will find the W twiddle by interpolating these points, a linear interpolation, as we did yesterday for proven existence. It's strange how it works. It's not working properly. Okay, now. So for that we will, there is a noise. Pablo, fíjate que apaguemos eso. Gracias. So we are going to see this sequence of these points. This sequence. And we can assume that the sequence of the ends is in this interval. So we have a map now from some set of numbers, finite set of numbers, to the reals, and we are going to increase this number. So this vector in the I coordinate is going to grow. We can simplify a bit the discussion by taking these intervals to be constants between these points. So we have that Tn is n minus 1 times delta t, so n equal to 1 is t0, and the delta is just this other formula, right? So here we have endpoints. So our approximations, this Win, go to from I equal to 1 to n. Okay. In practice, sometimes we don't do that. We just take some interval which is adapted to the conditions, the needs for the tolerance and the errors of the approximation, but this we can do later. We can explain later how to do it. But this is easy to have the formula simply. In particular, for some of the methods that we are using, we are just doing every step at a time, so we can put the delta t as small or big as we like. So how do we do these approximations? Well, what we do is basically Taylor's series. So we are assuming the solution has some smoothness, and therefore that the function has some smoothness. So what we do is to use Taylor series. So we approximate the value of y at t n plus 1 by the value which is this just with the value of the Elgar time Tn plus the derivative at Tn at y equal to Tn, and then the second term, the square terms, at some point, right, by Taylor's theorem. And so we have this approximation. Up to second order, we have this. And so this is what we do. We compute the Wn with the Wn plus 1, and here we put the value before, right? So what we are doing geometrically is we have our space, we have here a vector space. So we take some point, this is the point Wn. Look at the vector here, the f here, say this vector, this is f of Tn, of Wn, and make the step. So we go, say, from a point here to a point here. Then when we reach this place, we evaluate f here, f at Wn plus 1. This point is Wn plus 1. compute the f here, say the f here points this way, and so you go some distance delta t along this vector up to a new point, okay? So this is the algorithm. So suppose the true solution does something like this. We are approximating it like that. So we're making some errors. But the errors, because Taylor's formula, we know the errors goes to 0 like delta t squared in every step. So once we compute all this sequence of points, then we do some linear interpolation and compute the W twiddle. So from here we go to the W twiddle of t, right? But we never use this, we just stay here. So we want to compute the error, which we call the step error here, and it's the difference between the real solution at this time, Tn, minus the approximation at this time, corresponding to this time. And this, so for doing that, we use Taylor series, so we span this thing with the earlier time. Right, this is the Taylor's expansion up to here, keeping second order, and then we subtract the Wn, which is, because the Euler approximation is just this, right? So when you do this, you have here f of y Tn minus 1, and here you have this one, and you have a delta t squared. So look at this term here. These terms I can use Taylor series now and write it as at this step we don't need. We here just assume that the error at the En minus 1 error is 0, so we didn't have any error. So this term is 0 because this is equal to that, and this term is 0. So this step error is just some constant coming from here times delta t squared. And this constant is a maximum between 0 and t of the secondary derivative of y. So we can bound the error by the exact solution, the derivative of the exact solution. That means that if we know properties of the solution, we can have a value for r. And so we have that we might know this or not, but we can bound this probably. And what we are getting is that when we decrease delta t, the error goes like delta t squared. So here we have some examples. Say you take Euler's method for the equation, the linear equation. This is very important, this equation, to know what happens with this equation, the linear equation, because when we are dealing with problems, for instance, near a stationary point, we want to know the solution here. We saw yesterday that what we have to do is to study the linearized problem. So to study a problem d delta y to dt equals to the derivative of f with respect to y. Say this is I, component I, and this is component j, times delta ij. So, and this is a matrix, so we have this problem, basically this problem. So we know the exact solution of that is just exponential, and we can take and the exact solution, how it behaves. It behaves, here I did this, it behaves like that. So if there is no real part, we have an orbit, a closed orbit. If the imaginary, the real part is negative, we have an orbit that is decreasing, so we start here and go spiraling in. And of course, if it is positive, we have the spiral the other way around. So the solution starts here always and gets bigger. So we know everything about this. So this was the case, lambda equal to I, pure imaginary, we have cosines and sine. And here we did some plots. Remember, Pablo was talking about these things the other day. So this is the curve, lambda equal to A. So in blue is the curve, and in red is the vector field at those points. So if we try to do what we say with Taylor's expansion, the Euler's method, you will come here, so you will be getting a point further away from the surface. This point here will have a tangent vector which is also like this, so next point will be here, next point here, etc. So we'll have an increase in the radius. So it will act like we have some positive real part. So but of course, if we take delta t going to 0, you converge to this for finite times. Always convergence for finite time. So we now see this directly. The Euler's algorithm gives you this. Here I'm just putting lambda delta t wn. This was the f times delta t. So we get this in here. And this algorithm in particular we can integrate, say. So we can check that the solution of this is just this here. So you take the first value and you multiply by this number to the n minus 1, and you get this. And the local error now is like this. If lambda is imaginary, this is 1, so the error is bounded by delta t over delta t squared over 2. Now, we can compute this value for lambda equals to I, and you get this value here is given like that. So there is a plus and a minus sign, so you get 1 plus delta t squared. And this number is bigger than 1, right? So this number is going to grow with the power of this. And this is what we see here in the graph, just what we were seeing. In the graph, we were saying that the points will go further away, and so on. So we are departing So if you follow the points, you will get something like this. That is growing. And we do it now. We compute this and put on top. So here we did the calculation, and this is the exact solution, and the vector field here, and this is Euler's approximation. You see that it's growing. Why? Because if you take here the vector field is pointing a bit up from this point, so when you translate it here, it will be like this. So you have a growth. And this is pretty bad, because you cannot do very long calculations, because this growth is pretty bad. So you can check other methods which are of higher order. So we are not going now to discuss the higher order methods. So how do you approach in a better way? Well, one way to do this is to use just Taylor's expansion. Just expand this and keep higher terms, say up to cube here, delta t cube. And so now here you have here for instance you have a dy dt, you substitute by f, and here you have second derivative, so you substitute the second derivative, well I did it here. We have this derivative here of f also, so you use change rule. When you have this derivative, you derive with respect to y times the time derivative, and here you substitute this by f and you get this term. And if you take the second derivative and do the same, you get these two terms. So you have a second derivative times f squared, and then you have a first derivative squared times f. So if we put all these calculations inside here, what you obtain is this one. Sorry. This line here using Taylor's, and using the equation up to delta t cube, and so if we prefer to stay at delta t squared, we get this. So if we keep this term and this term, you get this algorithm. So Wn plus 1 is Wn plus, this is Euler's, this first thing, and then you have this. But of course, to compute this, you need to compute all the derivative of f with respect to y. So here there are two computations. You have to compute f in omega n, and then you have to compute this in here. And this might be easy or might be very difficult. Usually nowadays there are symbolic programs where you can compute this thing very easily, and then build the numerical functions to compute it, the real numbers. But sometimes it gets very clumsy, in particular if you take higher order terms, higher order approximations. And the local error is given by this. So again, it's a function of the solution, the exact solution. So we can make an example of this. Take our previous example, do the calculation now, and you have this part is Euler, but now you get this other part here. So you can write it like that, times Wn. So the solution will be this into some power times the first point, right? So you get this here. And now you can look at the amplification factor. So for lambda equal to I, and you will get this in here. So it's a bit better because it goes, the amplification factor is still bigger than 1, but not so big. If you take delta t to the fourth small, it's small, but still it's bad. Here, let me tell you why we are using lambda equal to 1, lambda imaginary. Let's see if I can draw something here. I think I have to go here. Yeah. Suppose, imagine you want to solve a partial differential equation. dt of u equals the x of u. Say in a circle, periodic boundary conditions. So one way of doing this is say, okay, I will take points here, equidistant points, and instead of solving for u, I will solve for a set of vector pi, and this I will replace by ui plus 1 minus ui minus 1 over delta x. The x is this distance. This is delta x. And this side, so I will get an equation like, I should put b here. Just the approximation. And on this side, then we will get dbi, for instance, dt is equal to this. So we approximated the space derivative by a finite difference center. So for the point here, we look at this point and this point, and so on. And so notice, this is a big system of the sort, if I write this as a vector, is a dvt equals to some matrix, because it's a linear thing, times a b, right? And this metric has some form, like, for instance, for the first one here, you have 0, 1, and minus 1 in the last one. And the next one is like this, minus. So you can build this matrix. But the thing is that this metric, all the components of this metric have a delta x that you can put, if you want, here. 1 over delta x, and this is a matrix like this, a numerical matrix. So, for instance, if you want to solve this using Runge-Kutta, you will say, okay, bn plus 1 now, the whole vector at time, this is the time now, will be like bn plus delta t over delta x times this matrix A of B component like this, and this is Bn. So notice that here you have, and if you diagonalize this matrix, so you go to another base where this is diagonal, let me call it B twiddle, where this metric is diagonal. So this metric diagonal is of the form 1 over delta x, and here you have things which are pure imaginary. The eigenvalues are imaginary. So you get something for the eigenvalues, We are going to do this calculation later on. For each eigenvalue, let's put j here. You get this plus some lambda real j dt over dx b twiddle n j. Okay? So here you get something which is imaginary. Right? And worse, when you want to take smaller times space steps, this thing is going to grow. So at most, in general, you want to keep this finite. So you make delta t go to 0 and delta x goes to 0, but keeping delta t over delta x fixed. Right? So you need that your algorithm has to work well within imaginary points here and with the amplification. This, remember, this is what enters in the amplification factor, which is rather, with this number, rather big. That's why we are very concerned with the problem of the amplification. So this is what we have to be checking. Is it clear? So we have imaginary eigenvalues and they don't go to 0. When delta t goes to 0, this doesn't go to 0. So let me see if I can return to, yeah. So this is amplification factor. Imagine for solving a wave equation, this will have here, this lambda will be not, lambda will not be I, but will be some number, finite number, times divided by the delta x, some c, let's say, this number. So when we look at this, here I'm missing a lambda. This is lambda here, to the fourth, to the fourth. And yeah. So we will get some number here which goes like 1 plus c to the fourth delta t over delta x over fourth. And this number doesn't go to 0. That's the problem. Sorry, this, so no, it's not like this. I have lambda, yeah, no, it's like that. So this number now is finite. It's not going to 0, and we will have some amplification. So this is not good. Still is not good. So if we can use Taylor's, but we have to go to higher orders. So now we are going to see some other methods. I mean, Taylor is not bad because you have to analyze every approximation, but it's not so bad because we can compute higher and higher derivative of f in a very efficient way using symbolic things. So it complicates the code because you have to, at some point, you need to compute several derivatives of f. Then there are multi-steps methods. This method works like this. Suppose you do the Taylor expansion. Everything starts always with the Taylor. You do the Taylor expansion as before. You get this formula here. We now go to the delta t to the fourth. And then this formula is for arbitrary delta t, so I can take delta t positive and delta t negative, right? So and then I can subtract. And if I take a delta t positive and do a subtraction with the delta t negative, some terms from here it will go away. In particular, if you take this difference, so you use delta t positive here, delta t negative here, and you subtract, then you get this term. So you see that the delta square is gone, so you have a method now, this one, where the error is delta tq, right? This is the error term. This is a term we are not considering. So we have a method. This is very good in principle, because why? Because you say, okay, I have to evaluate f. The evaluation of f is just 1, so you only have to evaluate, but every step you evaluate f1. The only thing is that now you have to keep in memory wn and wn plus 1. And of course, if you are solving something like that, we have few components, say 5 components, there is no problem. We are going to solve hyperbolic equations. This might be 1,000,000 components, so you have to not only to store 1,000,000 here, but also 1,000,000 here. But this is not the main problem with the multi-steps methods. The problem is that notice that when you start this method, you wanted to have omega 1, but for this method to work, you need omega 1 and omega 2. So because omega 3 will be omega 1 plus 2 delta t f in omega 2. Right? So to start, you need 2 points. So usually you take omega 2 to be omega 1 plus delta t f omega 1. So you use a Euler's method, for instance. You start with this and then you continue with this scheme. So you need 2 quantities here. And this means that you can have problems, because there could be that the algorithm has more than one solution. So let me show you in the example what is wrong with these methods. So if we use the linear equation, we get this scheme where mu is t lambda delta t, and this scheme has 2 solutions. You can plug this in here in the solution, and you will see that there are 2 values, a plus and a minus, s plus, and there are 2. These are arbitrary values, a's, and these are the 2 solutions, which are the root of this second order polynomial. If you write this as, if you plug this here, s to the n, s plus to the n, s minus to the n, plug here, you will get an equation for s, a quadratic equation, and from that equation you get these 2 solutions. So one way of obtaining this value then is using this for omega 1 and for omega 2. Right, this will be a plus s plus 1 plus a minus s 1 minus, and this one is a plus s2 plus square plus a minus s square minus. And from here you know all these 4 things, you compute a plus and a minus. So you compute a plus and a minus, and you put it here and you get a solution. But you notice that if you multiply the roots, right, this is, when you multiply the roots, you get this square minus this square, and this square is, so you get mu square, so this is mu square minus mu square plus 1. So this is minus 1. Yeah. So this is minus 1, it's not 1. So this means that if the absolute value of one of these is bigger than 1, is less than 1, the other is bigger than 1. Unless the absolute values of both are 1. So in this case, when it's just an imaginary number, a complex number of norm 1, it's okay. But in general, if this is not the case, and this is a particular mu, you will have one of these that is growing and one is amplification. There is an amplification in one of the factors. So the solution will take this bigger factor will dominate. And so the solution will go away from the exact one very fast. So these methods, you start computing, you don't see anything because probably the error is very small, the amplification is not so big, but after a while you go away from the solution and it starts to blow up when nothing is blowing up. So these methods are not very good. So what we prefer to use is what is called one-step methods. And let me show you how it works for second order. Here, here. So in Euler's method, we say, okay, we have a point here, a vector, the vector field, say, points this way. Then I go some distance up to here, look at the vector field, goes along this line some distance, and so on. Look at the vector field here, and go some distance here. So you build like that. But you could do the following, you say, okay, I take this point, I have this vector field here, I take not to delta t, that will be the corresponding point here, but I go half up to here. Here I compute the vector field. And so now I use this vector field, I translate it to here, so I will put it here, and move along this vector field the whole distance, so I will get this point. Okay? This algorithm is called the midpoint. So the algorithm is, first I go to a point W star, which is Wn plus delta t over 2 f of Wn. I compute in this point the Fw, and then I do this Mw n plus 1 is Wn plus delta t now, the full delta t times f in W star. And this I claim is a better approximation. You could do something else. For instance, you start with this point here, go, the vector field was pointing more or less like this, go the whole step here, compute the vector field here, take the average of these two vectors, that will be some vector which is in the middle of these two, so it's a vector like here, like this, and now do with this vector, put this vector here, and go through this vector a whole delta t, and so you correct this point. That will be you do the I start now with this full step. You do the start, then you compute f omega star, and then you do wn plus 1 is wn plus delta t over 2 times f wn plus f w star, this is n goes inside, plus w star. Okay? So the first, this one is called midpoint. So this one. And this here is called Ohoim, the name of the guy that invented it. So let's see now how it goes. Here. So this is a midpoint. So you first compute a K1, just this thing, and a K2, which is just you see, this is the value at the midpoint. So it's Wn plus 1/2 of K1, this is the whole step. And then you say Wn plus 1 is Wn plus K2. Use this one in the midpoint. This, as I say, is called the midpoint method or improved Euler. Any of these names is okay. So let's see how it works. And I claim that this is second order. We are going to do that calculation later. So we use also the linear equation as before. So K1 is just mu, which is delta t times lambda times Wn. K2 is this in here with the K1 here. And so the whole method is like this. And this you can write like that. So you see here we are, if you look at this, we are expanding e to the mu. Right? This is the expansion of e to the mu. Because the solution has a e to the mu, basically. So this is the same algorithm that you find in Taylor's expansion. But now you don't have this, the other spurious solution. So I think here we computed this algorithm, and you see these are the points, these are the vectors, and you have from here you have this vector here, you go, no, the vector is this one was a vector at this point, so you go up to the middle, compute the vector here, and you put this vector here and move here. So this is a solution. This is how the method goes. And this is Hoim method. So you get the K1 is the it's the same as before, but here you put K1, not 1/2. You put K1 here, and then at the end you do the average. So 1/2 K1 plus K2. And also have a local error order delta T cube. These are we are going to compute later on. Actually, you can consider all these methods. Here you compute K1, then you compute another K2 using some weight here. So this is how much you advance with K1. And then you do the average here. You take some A1 plus A2, K1, right? So you can think of this method. And if you look at all the methods, here for instance, the midpoint was this alpha 1, 2 is 1/2, the A1 was 0 and the A2 was 1, and the Holmes is symmetrical, so this one is 1, the alpha 1, 2, and the A1 and A2 are 1/2 each. So we now we can put all this, we'll do the error for all these methods. No, I have to go here. So how do we do this? We do the Taylor expansion here for an arbitrary function. This is the same as above. And then we use Holmes' method. We work out everything. We say this Wn plus 1 is Wn plus this, and this one was this one, and this other one was this. So you get this in here. And here I use this difference. I use Taylor series expansion for the F in this line, and then I collected this in here. And so you get, this should be Euler's, so the sum should be 1 because it's the first term. I'm comparing this with this delta t, and then I have the delta t squared, which is this here. So you see, I need to have a method that is third order, so it coincides with this. I need this to be equal to this, and this to be equal to that. And for that I have A1 plus A2 equal to 1. And here comparing this with this is just 1/2. So A2 times alpha to 1 is 1/2. And so if I satisfy these conditions, I get guarantee a method that is third order. So that's the way you build the methods, just comparing with the Taylor expansion up to some order. The one that is mostly used in many applications is a Runge-Kutta fourth, right? And that method has a K1, which is the same, K2, which is like the midpoint, so it's K1 over 2 here. But then you take another one, K3, which is with this one, you put here and compute again with this other vector. Compute again. Here H is equal to delta t. In many places, H is used instead of delta t because you have to write less. And so after you do these midpoints, you get the K3 and compute the whole step with K3, and then you average them in this way with some weight. So K1 plus 2K2 plus 2K3 plus K4, and this gives you a fourth order method. So the error here is delta t to the 5. Okay? Remember that this is an error in one step. If I take in many steps, the error, the number of to reach some some t fix, I will have to take n delta t steps, and so I'm going to lose one of this delta t. The error, the global error will be delta t to the fourth. Now you can look at the amplification factor of this, right? So any of these methods, at the end of the day, for the linear equation, right, for dy dt equals to lambda y, is something like this, with some a here to the end. And you can check, you can do this, you can find this a for this Runge-Kutta method of fourth order, and you will discover that there is a region, a nice region, where the absolute value of a is less than 1, and it contains the part of the imaginary axis. So in a plane where I have mu remember is lambda delta t, the region where the method has an amplification factor which is less than 1 is something like this. So this is imaginary axis. So it covers some part of the imaginary axis. So this is a very good method for solving hyperbolic problems. We will see more. We have another notebook computing the amplification factors. Let's make a break. Let's continue at 10:20. Huh? Questions? I move this. I don't know how to go back. I think I have to go out, back. Oh. I don't know what I did. Are there questions on the other side?
I have a question.
Okay.